I'm Sofia Lemons, and I'm here to talk about trading monotonicity for cost in beam search. This is work done in collaboration with Carlos Linares López, Rob Holte, and Wheeler Ruml. First, we'll talk about beam search in general. Then we'll talk about previous work and its relevance to this concept of the price of monotonicity. And finally, we'll look at two semi-monotonic algorithms which we have presented in this work called mono-floor and mono-onward. Beam search is a satisficing heuristic search algorithm. It limits the number of nodes selected to some fixed width, called the beam width, at each level. And because of this, it can often solve problems that are too large to be solved by other approaches. Here in the example shown, we see beam search with width 2. And you can see that at every level after the first, it selects and retains only 2 nodes from each level in the state space. This allows it to cut a sort of beam of limited width through a large state space. And we would hope that in an algorithm like this, we could trade increased computation time for better solution cost returned by increasing the beam width. However, in practice, we find that's not the case. When increasing the beam width, beam search sometimes returns worse solutions than it would have returned with a smaller beam width. And that's shown here in the Korf sliding tile puzzle number 88 with beam widths 30 through 1000. We can see that the solution cost as the beam width increases is sometimes better than at lower beam widths, but sometimes worse. And this leads to the opposite of the kind of trade-off that we would want. Sometimes we give extra time for computation and extra resources, and in return are given a worse solution than we could have gotten otherwise. In previous work, we've fixed this by providing the algorithm monobeam, which is guaranteed that as beam width increases, solution cost will be as good as or better than would have been found at lower beam widths. The monobeam algorithm selects nodes for each beam slot one at a time. So for each beam slot S, we consider only the successors of the nodes currently in slots 1 through S when selecting nodes to keep for the next level of the search. So when choosing for slot 1, we would find the successors of the node currently in slot 1 and choose only among them. Then we would retain whichever successors were not selected and expand the node in slot 2 to gather its successors. And for slot 2 at the next level, we would select among only the successors from slot 1 and 2. Because of this careful slot-based selection, monobeam with a width W is guaranteed to return equal or better quality solutions than any monobeam search with a lower beam width. One aside, in non-unit cost settings, in our previous work, we found that beam and monobeam often found very poor quality solutions or failed to solve these problems entirely. This is shown here in two non-unit cost variants of the sliding tile puzzle, where monobeam and beam either fail to solve many instances in the case of inverse cost or return very poor quality solutions in the case of heavy cost. And what we found was that using a distance to go measurement, D, rather than a cost to go measurement in these settings significantly improved beam search performance. For that reason, in the current work, we placed our focus on algorithms which use distance to go measurements rather than cost to go measurements. However, the main contribution of this work is addressing this issue of the price of monotonicity. Because of this careful cost-based selection, monobeam often returns solutions with worse quality on average than beam search. It provides this guarantee of monotonic improvement from the solutions that it is previously or would have previously found at smaller beam widths, but it pays a price for this in terms of average solution quality. And the question we address is, can we trade off some of this monotonicity to get better solutions from beam-style algorithms? The first algorithm that we present to address this is monofloor. It takes a parameter n in addition to the beam width to designate the size of the beam which will be non-monotonic in its behavior. It selects for the first W minus n slots in the same way that monobeam does, selecting for slot 1 from the successors of slot 1, for slot 2 from the successors of slots 1 and 2, and so on. Then it selects for the last n slots in the same manner as beam search does, significantly less restricted. It can select among the successors of any nodes on the previous level of the beam and does so in just a purely best first manner. Because of this, the solutions that are found in the first W minus n slots are guaranteed to improve monotonically with beam width, the same as monobeam. This prevents our solution quality from ever falling lower than this floor, even while the last n slots are allowed to explore in a more unrestricted fashion. Here we can see that beam search has that performance we saw before, in which it often is finding significantly worse solutions than it found at lower beam widths. Monofloor, on the other hand, has a sort of barrier to any worse solution being provided than the one that was found in the monotonic portion of the beam. It maintains this monotonically improving floor on solution quality. In our larger experiments, we ran experiments across 4 different domains: the sliding tile puzzle, the pancake problem, and 2 versions of Block's World. In the sliding tile puzzle, we used 5 different cost models: unit cost, heavy cost, in which the cost to move one tile is the number of that tile, square root cost, in which the cost to move a tile is the square root of the number of that tile, inverse cost, where the cost to move a tile is 1 over the number of that tile, and reverse cost, where the cost to move a tile is 16 minus the number of that tile. And in the pancake problem, we used 2 cost models: unit cost and heavy cost, where the cost to flip a stack of pancakes is the identification number of the pancake immediately above the spatula. In Block's World, we used the standard Block's World, in which blocks can be moved from one stack directly to another, and Deep Block's World, where blocks can be picked up and put down, causing solutions to be deeper down in the state space. When looking at average performance, we ran all algorithms with a variety of widths: 30, 100, 300, 1,000, 3,000, 10,000, 30,000, and 100,000. All algorithms were given a memory limit of 7.5 gigabytes and were run in C++ code, which can expand approximately 1.5 million nodes per second. The average cost versus time results for monofloor show the range of behavior which we would hope. That is, that monofloor's results tend to be in between that of monobead and bead. The solution quality is between those 2 algorithms, and that in fact, as n increases, the behavior of monofloor is closer to the behavior of bead search than to monobead, and vice versa. As n decreases, such as at n equals 30, the behavior is closer to monobead than to bead. We also measured the actual monotonicity of the algorithms in practice by using the rank correlation statistic, specifically Kendall's tau, where we ranked using beam width and solution cost under the assumption that as beam width increases, solution cost should decrease or at least stay the same. And what we see is that in the vast majority of cases, monofloor has a better rank correlation measure than bead, with rare exceptions such as in the 20 blocks world at n equals 300, where the rank correlation of monofloor is slightly lower than the rank correlation for bead. The other general trend is that as n increases, as we increase the portion of the beam selecting in this non-monotonic way, that the rank correlation decreases. The monotonicity of the algorithm decreases as we increase n. This demonstrates that monofloor offers one way to trade monotonicity for solution cost. The second algorithm that we presented to address this is mono-onward. It also takes a parameter n in addition to the beam width, specifying the portion of the beam that will be selected non-monotonically. However, it selects for the first n slots in a beam search manner, using best first ordering across all of the successors in that portion of the beam, 1 through n. Then, in the last w minus n slots, it selects in that slot-based manner as monobeam does. What this allows is for mono-onward to have the guarantee that for any beam width larger than n, the solution quality is guaranteed to improve monotonically as the beam width increases, because of the fact that this slot-based selection is being used from that point onward. We see that behavior in this example again on Korf puzzle number 88, where mono-onward was given an n value of 50. At the lower beam widths beneath 50, it has similarly up and down behavior like beam search, but once it surpasses that n value, it has the monotonic behavior that we would hope for, that a solution quality is retained until a better solution is found because of the careful slot-based selection. So in this case, after width 50, the solution cost always improves monotonically. Again, in terms of average solution cost versus time, we see the kind of behavior that we would hope for, that the solution quality returned by mono-onward is between that of bead and monobead, where increasing the n value generally gives performance closer to beam search, and decreasing the n value generally gives performance closer to monobead search, with rare exceptions where the selection of the n value has some impact on where the sort of plateau begins for the monotonic behavior, such as in the 20 pancake problem where n equals 100. The rank correlation measurements for mono-onward show even more strongly that mono-onward has generally very monotonic behavior. When the n value is 30 in all of the settings tested, we saw a perfect rank correlation value because the widths which we were testing were from 30 through 1000. But even at larger n values, such as 100 and 300, we saw rank correlations generally above 0.9 with an occasional dip to 0.8. So mono-onward offers another way to trade monotonicity for solution cost. In conclusion, we see that these two algorithms, monofloor and mono-onward, where monofloor provides a fallback solution, which monotonically improves as beam width increases, and mono-onward provides monotonically improving solution quality once beam width increases beyond the parameter n. These two new beam search algorithms have guarantees on their behavior, and we can adjust the strictness of the monotonicity of the algorithm to get better average solution cost. Thank you.